Hello, everyone, and thank you for joining the webinar. My name is Walter Gonzalez. Joining me is my colleague Raghu Raghavan. Today, we're here to talk to you about two new exciting DC arc flash products that can be used for battery energy storage systems, which are now part of ETAP 2024. The first product is called the DCC area curve, which are reference plots that can be used to represent a desired incident energy limit in TCC views, which can help streamline the selection of protected devices or the selection of settings for these devices, and also at the same time help attain reasonable incident energy results all during the protection and coordination phase of a project. We're going to go ahead and see how to get this done using ETAP 2024. Additionally, we'll also explore a new methodology that's going to go ahead and take into consideration the transient short circuit currents for battery energy storage systems to help consider things such as battery rising and decay time constants, and consider arcing phenomena such as arc elongation and conductor erosion, which play a big role in the estimating a accurate amount of incident energy for the DC arc flash analysis. Now, the concept of C-area curves was introduced by ETAP in the IEEE conference of PCIC back in 2019. This concept is the generation of a reference curve, as you see here in blue, where this reference curve is nothing more than a collection of arcing currents and arcing fault clearing times that represent a target or reference incident energy. For example, let's say my facility wants to target a exposure greater than 8 calories, then that would be our target incident energy. Now, taking into account that reference, the equipment input parameters, and of course, potential equipment input parameter variations, that is going to go ahead and build a large collection of data points, and eventually, of course, that would really have a bounding lower limit and an upper limit. And what we will basically use this curve for is to coordinate against our protective device tripping curves. Similar to the way you would coordinate against a transformer damage curve, this is now a curve that represents an incident energy exposure. So we're able to use this to help us select the appropriate settings, perhaps even select the appropriate devices that will help us attain basically the requirements of protection coordination guidelines, and of course at the same time factor in a reasonable amount of incident energy for our equipment. Now, to understand this concept a little bit better, let's take a look at all the various inputs that will dictate how that clearing time is calculated, which are going to be, of course, based on the various calculation methodologies out there, such as the max power method, Stokes and Opperlander, Packard methods. Regardless of the method you use, we have to look at which input parameters help create those fluctuations in the arc flash results, right? Which, of course, are going to be the system voltage, the fault current, the electrode orientation, the gap between conductors, the enclosure dimensions, working distance, and of course, all of that with respect to a target incident energy. Now, it's not sufficient to look at just knowing what input parameters vary that. We also have to take into consideration if and when there could be fluctuations or variations in each of these inputs. And that's because, of course, a lot of the systems, of course, are not going to be static, right? Different operating conditions, different maintenance practices, and various things that are, of course, going to create potential fluctuations, right? So we need to make sure we carefully analyze and can identify are there voltage variations, fault current variations, variations in conductor orientations, gaps, closure dimensions, and of course, working distances, right? So to better understand that, let's look at a couple of examples. Now, voltage can be, of course, one of the key items that can, of course, vary. Now, depending on, the equipment, data sheets, different, industry practices, and of course, guidelines that are out there, the voltage variations will be different for each type of system. Now, there are references out there, for example, the IEEE 946 does publish typical voltage variations. For example, they list for equipment rated with a nominal voltage of 250 volts, the potential typical voltage variation of plus 11 or positive 11% or a negative 17% reduction. Now, there's also the consideration of the type of equipment we're dealing with. For example, of course, talking energy storage systems, we're talking about lithium-ion batteries, right? Of course, based on the current state of charge, we do have a fluctuation in voltage, but we also in turn need to recognize that this state of charge is also going to indirectly affect our fault currents, which is another key player in this, right? As we look at these variations that, whether it be a state of charge or it be the characteristics of the type of, source we're dealing with, or of course the facility operating configurations, all these different things we want to keep track of because they create variation in the fault current. And what that basically does is establish a profile of fault currents. So when we establish the range of a maximum and minimum fault current, what we're really doing is we're building the building blocks of the range of arcing currents that can be present at our fault locations. Now, of course, in addition to that, we have the electrode orientations or configurations. For example, in this sample piece of equipment, we can identify a horizontal parallel orientation here, but in the same piece of equipment, we can also identify a vertical parallel orientation. The reason why you want to pay close attention to this is because the orientations here can also play a role in different arcing phenomena such as arc elongation or conductor erosion. So again, another piece to the puzzle that helps add more variations into our solution. Now, in addition to that, we also have the gap between conductors. Again, within one single location, we could have a single gap as you see here, or depending on where the arc initiates and lives, we can also have the potential of a different gap between conductors. Now, as everybody probably already knows, as that gap varies, that's introducing some fluctuation in how the arcing current is developed, right? Depending on how large or small that gap is. Now, in addition to that, you could also be facing variation in enclosure dimensions. For example, combiner boxes, right? Where for battery energy storage systems, even if it's not too common, you could take advantage of this when perhaps you're in the, design phase where you're perhaps looking at different vendors and you want to take into consideration, the different layouts and potential variations in equipment dimensions, or you could also build a family of C area curves to cover a range of potential enclosure sizes at a particular facility. But again, this is something that we need to do on a case-by-case basis as applicable, right? Now, the last but not least input parameter that we need to take into consideration, of course, is the working distance. Now, this one is probably pretty obvious, right? Depending on, the work practices and the inadvertent movement from the worker, we could potentially either be increasing or decreasing that nominal working distance. So we want to make sure we factor that into our curve because, again, the farther away we get away from that device, the less exposure we have, but the closer we get, of course, that works against us with a higher incident energy exposure. Now, to better understand this, let's go ahead and switch to ETAP to see how we can go ahead and make use of these curves and generate them using ETAP 2024. Okay, we now have ETAP 2024 open, and as you can see, the user interface that has changed significantly. So let's go ahead and explore how we can navigate to the DC arc flash mode. Let's go ahead and locate the arc flash group, which is down to the left. Then we have to go into the arc flash tab of the ribbon bar and locate the DC arc flash analysis mode. Now, let's go ahead and enter the battery energy storage container so we can look at the battery system we're going to go ahead and analyze. Now, as we enter this location, what we want to do first is confirm a couple of things in our study case. So let's go to the analysis section of the toolbar, open the study case, navigate to the method page, and first, of course, we want to make sure that we set up all of our preferences of how to model the sources and so on and so forth. Next, on the method tab, we want to make sure that we have the desired arc flash methodology, for which the areas can be based on either maximum power, Packard, and Stokes and Opelander. However, based on different publications and comparisons and actual arcing events, the industry is most comfortable these days with the use of the pocket and Stokes and Openlander method at this time compared to the maximum power method. But of course, based on your engineering judgment, that selection of methodologies is done, to which we're going to base our C area curves on. Next, we need to make sure the update IBF to bus option is selected and enabled along with the maximum minimum option. This option is going to be used to update the fault currents for each of the faulted buses. Now next, we need to establish the combinations of calculation we want to consider for the fault locations. For example, here at the inverter combiner box and DC combiner for the batteries. So I'm going to go ahead and go into my scenario wizard where I have pre-set up two conditions to consider the range of fault currents in my particular sample system. First, I'm going to go ahead and consider the maximum state of charge as one condition. So let's go ahead and hit run. Now, every time that you execute that calculation, you're going to notice that if you go into the bus editor and the arc flash tab now, you're going to, of course, have the amount of fault current that's available at the fault location. Now, in the new tab that's added called the protection tab, you're going to also have a new section that stores the maximum and minimum fault currents. Of course, right now, since I've executed a single calculation, we only have a single value for both max and min, but that will change the moment I execute more calculations. Let's see that next. I'm going to go ahead and open the scenario wizard one more time using the study wizard shortcuts. I'm going to go ahead and execute now my minimum state of charge calculation to consider another fluctuation in the fault current as well. So let's go ahead and hit run. Okay, now let's go ahead and check the bus editor one more time. And if we navigate to the protection tab, we can now see that we have built that range of fault currents with the maximum stated charge approximately 102,000 amps, with the minimum stated charge approximately 92,000 amps. And as expected, these fault currents are in the higher range due to the nature of batteries, right? We do have a healthy amount of fault currents typically with batteries. Now, the next step to start generating our C area curves is to go into the arc flash tab, navigate to the TCC plot energy, select C area, launch the settings menu, and this is where we're going to go ahead and define the constraints for the C area curve. The constant incident energy is going to be my design limit. Let's imagine that my facility wants to make sure that the exposure at this inverter combiner box is no more than 8 calories. So that's what I enter there. After that, every other set of input parameters down below are going to be the tolerances I want to take into consideration. For example, let's say that I want to consider a 10% tolerance in the voltage. For example, the maximum and minimum fault currents, I can also consider tolerances, but for this example, I'm going to leave those based on the calculations that ETAP has already done. I can also consider additional electric configurations. Let's assume that for this particular example, we have the presence of vertical and horizontal configurations. And we can also, as an added bonus, consider the arcing phenomena as we were talking about earlier. Now, Raghu in his session will cover these in depth, so I'm going to go ahead and move past these at the moment so we can properly introduce those topics with transient arc flash. But again, keep in mind that if and when you want to consider them, the C area curve is powerful enough to consider that. Now, we can also consider tolerances on the input parameters such as gap. For example, let's assume a plus and minus 30% tolerance. We can also consider equipment dimension variations. For example, let's consider a 20% tolerance. Again, we can imagine that we perhaps are still in the design phase and are considering different vendors. Again, if not applicable, that would not be something you have to enter. And then working distance, we can of course enter let's say for example, a 20% tolerance. So now what this is going to build is based on the established range of fault currents, a C area curve that represents 8 calories, even when considering voltage, electric configuration, gap, dimensions, and working distance tolerances as specified in this editor. So now to generate the C area curve, I simply click OK on the bus editor and C area plot editor. Then I select the equipment of interest that I want to plot and look for the add star view group box within the arc flash tab in the ribbon bar, and I hit create star view. Okay, now that the C area plot has been generated, let's go ahead and zoom in on the TCT created. Now what you see here is the rectangular curve that we have been seeing in the presentation a couple of times. Now, of course, since the range of fault currents is not drastically different, the length of that area is not very long, but it is pretty wide comparatively, and that's because we are taking all the different potential percent variations into account, right? And here, what this area curve really is telling us is that as long as this curve is to the right and above of the clearing time or characteristic curve of that protective device, which in this case is the fuse, the instant energy release will be 8 calories or less. Now, of course, this is very, very useful when in the protection and coordination phase because, as you saw just a few seconds ago, in order to establish this reference curve, all I needed was a range of fault currents, which again, you don't need any arc flash knowledge for, and a set of couple of engineering assumptions for potential tolerances in the arc flash input parameters, which again, we can do with proper engineering judgment. And now, as I select my protective device curves, I can see that, for example, this fuse will be basically helping us attain that limited incident energy value. And of course, what helps us here too is the battery energy storage system has a healthy amount of short circuit current, which is also going to help us reduce those clearing times, right? But again, we have a nice, simple, but elegant way to view this reference curve, even without having to do a formal arc flash analysis. Now, and actually determine what the final value is, we do have to run that analysis, but using this tool, we no longer have to be surprised when we run those arc flash analysis and have to focus on a long list of locations with very, very high incident energies because we've done that work ahead of time during the protection and coordination phase of the project. So now let's go ahead and close this curve and let's do one more thing here. Now, if we go back into the one-line diagram, let's do a similar analysis for DC combiner box 1. Now, to avoid some extra data entry, I'm going to go into the Arc Flash tab. I'm going to open my C area plot editor, which is here in the TCC plot energy section. And I'm going to use my copy to default option on my DCC area plot editor. The reason for that is because I want to go ahead and take advantage of the same engineering variations that I have considered, and I can reuse that here in this editor. So now if I go into the DC bus, all I'm going to simply do is I'm going to go ahead and hit paste and bring in that data. That way I can take credit for that data that I have already specified for the other fault location with similar parameters. Now, one key thing to notice here is inverter combiner box 1 was a location with a single radial feed, right? Now, when using C areas for locations with multiple sources, we do need to make some adjustments in order to factor in that difference because, of course, we want to make sure that we use these curves appropriately. So the way we can do this here is to basically target the amount of incident energy that each of these sources should deliver in order for us to get a combined incident energy of 8 calories in this particular example. So to do that, I would simply use approximately, in my particular case, since I have a set of 5 batteries feeding that location, approximately a fifth of the incident energy target, which is approximately 1.6 calories per centimeter squared. Okay. Now, similarly, I need to make adjustments to my minimum and maximum fault current because this time around, it's going to be a fraction of the total maximum and minimum current that each of these batteries is going to see, or each of the batteries fuses will see, right? Luckily here, since battery systems are going to be, of course, very symmetrical, here in this particular example, all of the different fuses see the same amount of current. So here I can safely make an adjustment to consider a fifth of the total arcing current, bolted fault currents for the minimum and maximum. So what I do here is I simply ask the C area plot editor to consider 20% of the max and min so I can properly adjust them for the individual fuses that we're going to do an analysis on. So after I do that, I go ahead and click OK, and then Okay, now to generate the new C area curve for the DC combiner box, I'll go ahead and rubber band the bus and fuse for at least one of the batteries since the system is symmetrical as we saw earlier. So now let's go ahead and create the star view. Now once that star view is created, we can go ahead and focus here where the C area curve is located. Now, what we can see here is, of course, with the reduction in current, since we're looking at the individual batteries contributing to the combiner box, that C area curve has shifted to the left with our adjustments. But we can clearly see that this C area curve is still to the right and above of that fuse. And as expected, because the larger magnitudes of currents, of course, are leading to a smaller tripping time. Again, we still don't know the exact amount of incident energy that's going to be released at these fault locations, but we can go ahead and run a formal traditional DCR flash analysis next to confirm that the prediction of the C area curves is in fact accurate. Let's do that together. Let's go ahead and close the C area curve next. And let's go ahead and run the analysis. Now, using the ribbon bar, we can take advantage of the Study Wizard shortcuts, and let's go ahead and run the analysis through here. So I simply hit the drop-down menu, hit scenario 1, which is my maximum state of charge calculation. And as we can see here, as we zoom in, we're looking at approximately 1.4 calories at the inverter combiner box for the maximum stated charge and 3.4 calories for the maximum stated charge for the battery combiner. Now, in both of these cases, the C area constraints have held. We are less than 8 calories, right? Now let's put this to the test for the minimum stated charge. I'm going to go ahead and hit the shortcut again here in the ribbon bar, hit scenario number 2. Now we can go ahead and see what happens for the minimum stated charge. And as expected, of course, our fault currents have been reduced. Therefore, our incident energy only came down because we have enough amount of fault current to trip those fuses still in a rather quick amount of time. But in both cases, you're able to see that even though we never formally ran the analysis until right now, the C area curves helped us get a visual confirmation that based on the protective device that's connected to each of these different fault locations, our reference curve was able to guide us and let us know that we will be able to attain that target incident energy limit. Now, of course, depending on the different constraints that you may have, the process of doing this may change a little bit, but overall, we can see the benefit of how these reference curves can easily be used as a visual inspection during the protection and coordination phase as we pick protective devices for our design or as we are picking the adjustable settings, for example, for breakers, to make sure that as we consider protection and coordination criteria, we're also in parallel able to select settings that help limit the amount of incident energy exposure at each of these faulted locations to a manageable limit. Now, my colleague Raghu Varaghavan is going to take over so he can discuss another detailed analysis that can be done for battery energy storage systems using a transient short circuit analysis. Raghu, go ahead and take it away.
Thank you, Walter. Hello, everyone. This is Raghu Veera Raghavan from ETAP, and I would like to talk about the transient DC arc flash analysis for battery energy storage system using ETAP 2024. I'm excited to explain the concepts and go over the overall big picture on in this demonstration to explain the overall dynamics of the battery energy storage system, which is most often called as BESS, and with an example. So the agenda for today's presentation is to make sure that we understand the dynamics of the battery energy storage system. What are the short circuit characteristics that a battery could have and its associated elements, such as the effect of DC capacitors and motors that is included in ETAP? And what are the challenges faced in the arc flash calculations, and how the transient solution is one of the most accurate and sophisticated methods to determine the time-based arcing current, and also to consider other effects of arc flash such as arc erosion and elongation with a step-by-step demonstration of the ETAP software. The previous part of the session, Walter briefly described about the probabilistic variations of the equipment, the short circuit characteristics, and the maximum and the minimum short circuit current, and how it is being used to determine a constant energy area in order to evaluate the operation of the time current device. Now, in this part of the, the presentation, I would like to explain, yes, you're going to get the maximum and the minimum short circuit current, but what kind of short circuit current is that? Is that based on the actual steady state characteristics of the battery, or also based on the dynamics of the battery energy storage system that involves in a different levels of battery management system connected to the corresponding devices, right? A typical example that I would like to explain on a battery storage system installation is it particularly has a battery, a AC to DC converter or a rectifier, and also controls to basically evaluate the need for the demand that the utility cannot be able to supply in the event of an actual peak loading condition. The key aspect of this particular battery storage system is it is connected to the utility and at the same time provided with the power either from a renewable source like a PV arrays. But however, the management system does have controls in order to provide load demand in case of any load peak is being attained, so that in order to not overload the utility in terms of those participating conditions. A good example of new loads causing extensive peak demands to the utility is the electrical vehicle charging. Finding ways to meet this demand even with few charging vehicles can sometimes double the total power consumption of a facility. To supply the demand and to maintain a voltage of power in distribution equipment, an on-site storage solution is necessary. In this example, you do have a utility, a power distribution transformer, a distribution equipment, or a switchgear is powered with the battery energy storage systems. And when the voltage is within the tolerable limits, or if it's exceeding the tolerable limits, the battery gets to discharge in such a way that in order to compensate the voltage. The BESS helps to reduce and manage the demand, and its control help to discharge or charge depending upon the threshold limits. As more vehicles pull up and draws current, the BESS helps to discharge to keep the system stable. In the absence of load demand, the BESS gets charged back to prepare for the next cycle. So the reference point is actually determined within the feeder location, and in order to discharge or charge the battery, so the controls will operate within the given threshold limits. The dynamics of the BESS can easily be simulated in ETAP using this project that I have created, which can do the load flow analysis to perform the charging capacity of charging electrical vehicles, and how the battery management system could discharge or charge depending upon the threshold given into that feeder bus that is connected to it. So in this case, the inverter combiner box is taken as the reference voltage of maintaining the voltage within the threshold limits that can be defined in the load flow study case for under voltage and over voltage condition. And I have created three scenarios. In the first scenarios where I did have the opportunity to say that, okay, when there are no electrical vehicles available, the battery is actually charging itself. So this could be achieved using the battery editor, where the battery management system could actually be set in order to charge or discharge depending upon the voltage of that connected bus. So the first scenario where I did have selected that there are no charger loads, no cars connected to the charging station, I have the ability to run the load flow to perform the charging condition of the battery that is provided by the utility. So in this case, when you run the load flow, the battery is actually charging and it is providing the enough amount of the connection to the battery storage system. And during the second scenario, where I have the actual loads being connected to the system, as if the concept of all the chargers available right now and all the charging stations are in use. As you can see, the voltage of the equipment starts to decrease because of large drawing of current and power, and that would cause a low voltage condition here. In this case, the battery is now discharging towards the inverter combiner panel, and it is obviously trying to inject current in order to not overload the utility that is going to be connected to the same facility. The option to include DC capacitors, and the modeling of the DC capacitors is new in ETAP, and that could also provide some voltage compensation on top of whatever the battery discharging capabilities are. So for that scenario, in order to overcome the alerts of the voltage, I have created the scenario number 5, which would actually provide you that 4 charging vehicles are in place, batteries discharging to avoid the overloading of the utility. Now we also have the on top of it to have DC capacitors to regulate the voltage. So when I load the scenario, the capacitor is on, and depending upon the ratings of the capacitor provided by the manufacturer and the number of cells and the number of packs and the voltage across the capacitor is enabled, the program automatically enables the effect of capacitance and also regulates the voltage within the acceptable limits. And by achieving this, the battery is of great help with the controls available to discharge the currents that is required for the loads that is within the charging station. Now that we understood the dynamics of the load flow analysis done using the battery management system, it is now important to analyze the short circuit characteristics of all the elements available in this system. We can start with the battery and then go to the loads and then the capacitor itself on how the short circuit characteristics are determined based on several available industry standards. Now, the first thing is the battery storage system in ETAP and the libraries associated with the batteries, they all come with a proper state of the charge characteristics provided by the manufacturer, which can be either estimated or entered based on the available data provided by the manufacturer or through industry standards. We have dedicated libraries that is available in battery storage system here, where we can be able to select whether it's a lead acid or a lithium ion and be able to select the parameters and to establish whether to have a proper discharge voltage curve as a function of voltage in order to see how much the state of charge is actually provided to the actual equipment. Depending upon the state of charge, the program will automatically enter or inject current to the system, and on top of that, it also takes into factor on different rising and the time constants that is required to perform the actual short circuit characteristics of a battery. The short circuit characteristics of batteries can be referenced from the IEC 61660 standard, and it does include all the circuit that is required for the internal resistance during charge or the internal resistance during discharge, the external cable resistance, internal inductance, and external cable inductances respectively. And depending upon the input parameters entered in the impedance page or the rising time constant and the decay time constant, the program automatically uses these equations to determine the actual time current characteristics for the battery depending upon the different time constants and evaluate the short circuit current, which is nonlinear, and it is at the same time based on the time constants entered in the battery editor. So for example, in this case, we did have this curve shown here. This slide shows that the battery current, the IK, which is available here, will be the steady state current, the steady state short circuit current, and it is typically determined after 1 second duration to allow the current to rise past its peak point and decay enough to obtain this value. This plot also shows the time to peak and rise and the decay time constant respectively. The point in the time marked as Tk can be considered the fault duration. And this is the time we'll be using to determine the incident energy. Similarly, the standard also provides good references on other elements in the DC power system, such as a DC capacitor. And the DC capacitor also has its charging current and the resistance across the capacitor, which could be entered in ETAP editors depending upon the manufacturer data. And the current to time relationship based on the resistance and the charging current can be calculated by the standard, and it is also being simulated in ETAP based on the peak charging time and the peak current associated with it. And this current associated with the battery current would give us the most updated profile of the short circuit at a given fault location. Last but not least, we can also have the motors or the DC loads modeled in ETAP using the motor circuits provided in the standard and the corresponding armature resistance, inductance, the time constant, and the shunt field resistance, the inertia, the torque. And based on those mechanical and electrical characteristics, the program will still evaluate the rise time of the motor and its peak current and the steady state current, which is again added to the short circuit profile, and which will give us the overall short circuit at that particular location with interaction of the batteries, capacitors, and the loads respectively. Now that we understood the short circuit characteristics of the battery, capacitor, and the loads, it is now important to visualize how it is handled by ETAP in the short circuit calculation. So for instance, I created the first scenario for short circuit called scenario 6, where we could see the short circuit effect of the battery only with no loads and no capacitors involved. So when we try to simulate this, we have the ability to specify the duration of the short circuit, the Tk, and then the time step for each short circuit step, where the program calculates and gives us a graphical plot based on the characteristics of the battery that is being entered in the editors. So if I run the short circuit scenario number 6, the program does give you the overall combination of the short circuit profile on all the batteries involved, and we do have this plot option to generate the plots for the corresponding faulted location. So we do have the ability to show the positive, the negative, and the charging ones, and the curve automatically provides the profile of the short circuit current that we can be able to establish based on the input parameters entered in the battery. On scenario 7, I have included the effect of the loads with the charging batteries, and that includes the characteristics of the motor curves in the short circuit, and the corresponding currents would be reflected in the short circuit profile accordingly. The magnitude will change according to the effect of the loads that is being considered in this simulation. And on top of that, we do have the last condition where we have the 4 charging vehicles, batteries discharging, and then we do have the DC capacitor to as a short circuit point of view. And when we run this particular calculation, since the capacitors do have longer rise time, a shorter rise time, so it is also be useful to adjust this time step to see the profile of the short circuit with the capacitors involved. Depending upon the conditions of the system and the fault location, and the corresponding capacitance effect can be graphically plotted. As you can see, there is the effect of the capacitance of short circuit and followed by the battery short circuit profile within the given time frame. Now that we understood the short circuit characteristics of all the sources and the loads, it is now jump into arc flash challenges faced in the battery energy storage systems. As Walter mentioned in the original presentation of the DCC areas, the equipment variations are unknown. For example, voltage variations, electrode gap, the electrode conductor orientation, and the limited battery data that is available, which is kind of like a black box where the internal resistance is not known. What are the variations in the fault currents, and what is the physical characteristics of the equipment? How we are going to tap all these things unknowns as a challenge to get the necessary and the most optimistic solution for DC arc flash analysis. What is the arcing current at the device operating time? Is this the steady state current at Tk is equal to 1, which is at 1 second? Is that current same enough throughout the operation of the short circuit and arc flash? Is the IARC accurate based on the battery short circuit characteristics, including the rise time and the peak time? Or is the IARC or the arc current enough to burn the copper conductors before the protective device trips? What if you have a fuse or current protective devices that are operating in a current limiting action? What is the magnitude of the current? Is that current used to determine the energy? Well, the ETAP 24 includes the features to improve the calculation of DC arc flash, keeping those challenges in the mind. All right. So, for example, the same battery short circuit that we determined when we introduced the arc resistance based on the arc flash, now we determine the arc current characteristics of that same faulted location with the current as a function of time. And this current is again based on the dynamics of the battery and other associated elements, and it will give us a clear profile of the arc current at a given clearing time. The arc flash equations can be applied by using the iterative solutions, for example, Stokes and Oppenlander method, and we can determine the arc current as a function of time using the bolted fault current from the battery short circuit as follows. Introducing the arc resistance and the voltage across the arc as a function of time can give us the arc voltage and the incident energy in a time current plot using those equations. In this application, I can be able to show the arc flash analysis of two different locations that are of interest. One is actually the fuse disconnect location and the other one is the inverter combiner box. Now, the first part is if I have to run the regular arc flash based on the regular Stokes and Oppenlander method, I do have the regular arc flash calculated at the time at which the protective device clears, and or it could be 2 seconds or any clearing time determined by the program or user defined, but the current calculated to determine the clearing time and the incident energy is based on the total current at the fault clearing time. And this current is on a steady state level, which does not include the battery short circuit behavior. So in this case, if I run the calculation based on the regular settings, you could see the incident energy on the fuse disconnect location as well as the inverter combiner box location. Now if we introduce the transient arc flash behavior, where we do enable the transient methods based on the duration and the time step defined, I have the ability to run the short circuit calculation first with the battery characteristics and then evaluate the arc current as a function of time. And this arc current can be able to determine the energy based on the time at which the actual protective device operates, or even perhaps a current limiting action feature could be enabled on the fuse to reduce the incident energy at that time at which the fuse is limiting the current. In this case, if I run the transient arc flash, you could see that by running the transient arc flash, the program determines the incident energy based on the realistic value of the current and the time determined by that particular arc current. So we can be able to graphically take a look at it using the transient behavior of the fuse disconnect and the combiner, and we can be able to show the actual operation of the current, voltage, arc energy, and the incident energy accumulated over the time. And this plot will give us a clear picture on how the short circuit current is originally calculated, and based on that, what would be the arcing current at a given time. And let's say the fuse operates at the time at which the actual arcing current is happening based on the battery short circuit currents, and we can be able to determine the incident energy at that given time, which in this case it says 0.990 at that location. However, the overall clearing time would be able to be determined at 0.01 seconds, which comes out to be 7.72 calories. This is more accurate. This also gives you not an overly estimated incident energy, but at the same time sticks on to the the actual battery short circuit performance and the corresponding arc current associated with it. Another important concept that would be of good interest to us is the concept of arc elongation and erosion of the conductors. What does that mean? So these battery locations can have a very high arc current, and obviously at the time of the initiation of the arc flash until the arc flash continues to self-sustain, there is a possibility where the arc can extend over its column using the elongation effect. And that elongation effect could cause more incident energy accumulation based on the dynamics of the arc that could take place in a physical manner. On top of that, another important concept is called the arc erosion, which we can be able to take a look at it based on the physics of the arc and the conductor material and its cross section. In this case, let's say we have a copper conductors with a specific cross-sectional area or a conductor size. Depending upon the high magnitude of the arc currents, which is noticed in battery storage systems, that large magnitude of current could possibly burn the electrodes or erode the electrode material, thereby causing a very high or a longer gap, and which would basically increase the arc voltage and have an effect on eroding the conductors, and this could possibly affect the incident energy as well. And this erosion effect can also happen way before the fault clearing time determined by the protective device could even take place. And this is another value addition to the incident energy calculation. The concept of arc elongation and erosion can still be demonstrated in this same example using this scenario number 11. So in this case, I have enabled the actual apply elongation effect and also the erosion effect. As you can see, once the erosion effect and the elongation effect is included, the same plots between those two conditions with and without erosion and the calculation of the arc energy, voltage across the arc current, and the incident energy will have a different spectrum of energy that could be easily documented. As you can see here, the arc has actually enabled and extinguished in a fairly faster location here, and that would give you like around 11 calories for the fuse disconnects location as well. So this overall graphical representation clearly helps us out on how the dynamics of the arc put together with the dynamics of the short circuit of the battery systems, the DC capacitors, the DC loads, could be an ultimate solution for arc flash in accurately estimating the incident energy rather than printing arc flash labels that are overly conservative. So the conclusion is you are running arc flash analysis on your DC arc flash battery or energy storage systems. Yes, you print arc flash labels and you do use the conventional methods that ETAP already has. But this method of using the transient arc flash analysis is a very good add-on to justify how the dynamics of the arc and the physical behavior of the arc, such as elongation and erosion, could impact the final calculation, and how to evaluate the incident energy based on accurate fault clearing time. And these graphical plots would be of great use to help you to determine whether to print the correct arc flash label is already in place based on considering these dynamics and the transient arc flash behavior. With that, on behalf of myself and Walter and the entire arc flash team, I thank you all for attending this webinar, and we look forward to provide your feedback and questions